So today we come back to our new definition of the area under a curve. It's given by this limit, okay? Area is equal to the limit as n approaches infinity of the sum of I equals 1 to n of f of ci times delta x, where again delta x is b minus a over n, the endpoints b and a, divided by n, the number of rectangles. Ci can be any point in an interval, and then the function of ci gives us the height of the rectangle, okay? Taking the limit as n approaches infinity says we have an infinite number of rectangles, okay? So we find that this is an exact area of a region in a plane, okay? So, example 6. We're finding the region. This is slightly different than the problem we did yesterday because our region is different. So yesterday it was from 0 to 1. Today we are finding the area bounded by this graph, which is an upside down parabola, the x-axis, and then between x equals 1 and x equals 2. Okay, so that's slightly different. So if I graph that, 2, 3, 4, 1, 2, it looks like that. But the region that we want to find the area of only goes from 1 to 2. All right, so we're only finding this area, and we'll see how that changes the way we write out our definition here. Okay. The first thing that we would like to do is say that we're going to divide this into n subintervals. And again, that's delta x. Okay, delta x equals b minus a, which in this case is 2. b is 2, and a is 1, divided by n. So 1 over n. Delta x is 1 over n. Okay. We call that partitioning. Okay, partition means put into different parts. Okay, so we partition into intervals of size 1 over n. Okay, so that's the width of each rectangle. Now we have to choose a point in each interval, and in general, the right endpoint is the easiest, right? In our previous examples, the right endpoint was always delta x times I. Okay, that's still true, except we need to note that we are not starting at 0. So when I is 1, okay, instead of getting 1 over n, we need to get 1 plus 1 over n. Okay, 1 plus 1 over n. So we have to have our a, whatever value we start with to begin, plus delta x times I, which when we had graphs that started at 0, we still had that, but it was 0 plus delta xi, which is just delta xi. So in this particular case, it's 1 plus I over n. 1 plus I over n. All right, so by definition, by our new definition up above, our area will be equal to the limit as n approaches infinity of the sum of I equals 1 to n of f of ci, which in this case we're saying is 1 plus I over n times delta x, which is 1 over n. Okay, so now we plug in. As we said yesterday, this whatever we are left with inside these big brackets, our summation, should be a function of n, but not have any i's in it. Okay, once we do the sum, simplify the sum, we should not have any i's left, but we should have n's. Okay, all right, so plugging 1 plus I over n into our function up here, 4 minus x squared, we get the sum from I equals 1 to n of 4 minus 1 plus I over n all squared, and then still our 1 over n multiplied. Okay, next step, simplifying that out, limit as n approaches infinity. Okay, sum I equals 1 to n, 4 minus, all right, the first term is going to be a 1. And note this minus applies to everything in here. So first term is going to be a 1, and then we're going to have a 2i plus 2i over n, and then a minus I squared over n squared. Okay, all times 1 over n. Okay, I'll make some color distinctions here. So this is what our limit is being applied to, and this is inside our sum. Well, this is our f of ci expanded, and then everything else is inside our sum here. Okay, all right, so simplifying once more, we get the limit as n approaches infinity of the sum from I equals 1 to n of 3 minus 2i over n plus, nope, sorry, this is supposed to be a plus. I apologize. This is supposed to be a plus. Okay, so minus I squared over n squared. All right, all of that times 1 over n. Okay, so now we can look at this in several different parts. Okay, this term does not have an I in it. These two do. And luckily they're just I and I squared, which are both things we can replace using the formulas we have if we simply factor out the constants. So within the sum, n acts like a constant. Okay, while we're dealing with just the sum, n acts like a constant. Once we start taking the limit, n acts like a variable. Okay, so for this first part, taking the sum, limit as n approaches infinity, the 1 over n can come out to the front. We're left with the sum of 3 minus the 2 over n squared can come out front, the n from there, and then also the multiplied n from there is where that comes from. And it's just an I, and then minus 1 over n cubed, same thing, the n squared from here, and the n from there multiply, and then sum of I squared. And this is all from 1 to n. Okay. All right, and then taking each sum individually, we end up with the sum of 3 from I to n will just be n, right? So n times 1 over n is just 1, so we're left with a 3 there. Okay, the next one will simplify to 1 plus 1 over n. Again, going back to our formulas that we need to know, okay, for the quiz on Wednesday. Okay, and then the last term simplifies to 1/3 plus 1 over 2n plus 1 over 6n squared. Okay, so now we're ready to do the limit. We got rid of the sum, we got rid of the i's, we have only n's, time to do the limit. This is where our handy property that the limit as x approaches infinity of 1 over x equals what?
0.
0, big fat 0, okay? So every term that has a 1 over n, or 1 over n squared, or 1 over n cubed, or 1 over n to the 4th, or 1 over n to the whatever, goes to 0. So that term is 0, that term 0, that term 0. All we do is add up the terms that do not have a 1 over n, which leaves us with 3 minus 1 minus 1/3, which is 5/3. All right, and that again, going back to our original goal here, is the area of this purple region. This area is 5/3. That's what we just determined. Not bad? Do you believe me that it's 5/3? You just blindly trust that it's 5/3?
Yes, maybe.
Yes, maybe.
Can it feel good?
Yeah, because the calculation is
The-
right.
The calculation or,
The calculation is right. I
okay,
think so.
okay. All right, think about it graphically. Right, if you had to break this into cubes, right, this would be, actually I didn't quite draw it correctly. So, all right. It would definitely be bigger than 1 and less than 2. So 5/3 is a pretty good approximation at least. But what we're saying is that that's exactly the area, okay? Okay, this is the same kind of problem, just a little more complicated because we switched the variables. But when we're done with this problem, we can go back to example 5 and compare the two results and see what happens here. Oh wait, I'm sorry, not example 5. Example, nope, not that one either. Oh, I'm sorry, there's it's a homework problem, okay, that you go back and look at, okay. Okay, so example 7. Now, we are given, once again, I'm going to write our formula for area up here. What is area? The limit as in approaches infinity. What's in?
And is how much rectangle?
Good, the number of rectangles. Of the sum from I equals 1 to n of what?
F of the I.
F of ci
Ci.
times
Times the delta x.
delta x, where delta x is
B minus A over N.
b minus a over n. What is b?
B is the right point.
Good.
Point.
The right endpoint and a is the left endpoint. Excellent. Okay, the area of the region this time we want to find is the graph of f of y equals y squared. The y-axis between y equals 0 and 1. Okay, so let me draw this for you. F of y, a function of y. It looks just like f of x squared, okay, but y squared is curved this way instead, okay? And at 1, 1, it ends, okay? Now, we want to find the area between the y-axis and this function. That means over here, between 0 and 1, okay? So this is what we're interested in. What is this area, and what would you describe that area? What would this function be if it were a function of x?
It's be like this.
No. Okay, we'll talk about that later. Okay, so here's how we set it up. It's the same way. Okay, now we're considering rectangles coming up from the y-axis, okay, instead of from the x-axis. Okay, so I'm not drawing these the best, but there's some, okay? So, all right, so we need to come up with a way to explain these, okay? All right, we can use the same basic procedure starting with what is delta y? Well, delta y is going to be the same as what we've seen delta x, the endpoints, right? Subtract the endpoints, divide by n. So in this case, the endpoints are 0 and 1, so it would just be 1 over n, right? So delta y, 1 over n. Now, instead of left and right endpoints, we can talk about upper and lower endpoints. Okay, so we need to come up with an expression for either the upper endpoints or the lower endpoints. Okay, which one of those is going to be most similar to the right endpoints? Remember, right endpoints are a little bit easier. Remember, right endpoints are the ones that at I equals 1, they are not 0. Right? So which would be 0 or at the beginning? Which one would be 0? The upper endpoints or the lower endpoints? Is 0 part of the upper endpoints or the lower endpoints? 0 is below, so it would be lower. Okay, so the easier ones to represent
That one is lower, that one is upper.
are the upper endpoints. Okay, and the upper endpoints are going to be able to be found the same way right endpoints are found, delta x times I. So in this case, they are I over n. Okay. All right, so now, and if we plug in those, into our function, we'll be able to find what we need to find, okay? So writing out our area now in terms of y instead of x, okay? Our n stays the same, all right? So it's still the limit as n approaches infinity, okay? And now we have the sum from I equals 1 to n of f of ci times delta y instead of delta x. So plugging in, limit n approaches infinity, sum I equals 1 to n. Plugging in I over n to our function y squared. So that would be I over n all squared times delta y, which is 1 over n. Okay, so we're taking the limit of all of that. Okay. So, simplifying, this one's pretty easy, right? So, the limit as n approaches infinity of the sum, take a look, this square will square the I and also square the n, and then we can factor n squared and n out to the front for n cubed. Okay. We're okay? Okay. And now we've got a really simple sum. Okay. We need our summation formula for the sum of I squared from I equals 1 to n. We plug in.
Can I go close?
Yeah, go ahead. So the limit as n approaches infinity of 1 over n cubed times the sum, which is n times n plus 1, that's a plus, times 2n plus 1, divided by 6. Okay, I'm going to jump over here. Multiplying that out, you'll find in the long run, the only term that matters is the term that has an n cubed on the top, because any other terms are going to be left with an n on the bottom, and we just saw if there's an n on the bottom, that term goes away with the limit. Okay, so I'll write it out though. Limit as n approaches infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. Okay, so taking the limit, okay, this term goes to 0 and this term goes to 0 because there's an n on the bottom. Final answer is 1/3. The area of that region is 1/3. Okay, so if we go back to it, this area is 1/3. So let me ask again, what about this area? What would this area be? If this is 1/3,
2/3.
this would be 2/3. That's what we expect. And if x equals y squared, how would you write that as a function of x instead?
Y equals, what is that called? A square root of x.
Square root of x. Okay, so we would expect the area of the square root of x from 0 to 1 to be 2/3. And I could have sworn that we did that in an example somewhere.
Yes.
Did we do that in the first example?
No, it's 27.
Oh, it was your homework. Okay. And do you remember what you got?
0.768.
Zero.
0.518. That's what I get.
0.768 and 0.518, because you did approximations. What is 2/3 in decimal form?
0.6666.
Okay, and so is that between your two answers?
Yes.
Yes, okay, so that's what we expect. All right, and that is it for 4.2. We are done. We're going to do some practice problems.